Welcome to another episode of sort of Science Matters, right? To actually explain some science that's sort of current, or at least still in the mainstream of discussion. I've been talking a lot about various Nobel Prizes over on a different playlist. Check it out if you haven't. It's pretty cool stuff. Today we're going to be talking about the Drake equation. The Drake equation is this fun equation that explains how much life is out there in the universe and can we talk to it, all that kind of fun stuff. So, are there other intelligent races of beings out there? And the Drake equation is supposed to be one that convinces you there actually are. So let's take a look and figure out what the heck it actually is. The Drake equation says multiply all these factors together and you'll figure out how many other uh, intelligent races there are inside our galaxy. It doesn't deal with other galaxies, it only deals with ours. Now, one thing I would criticize about this equation a little bit, if it were me, is this equation is supposed to be for people that aren't scientists, and yes, scientists also. But you see all these little subscripts. These are, FP, F1, Fi. Those are all different variables, nothing to be scared of. But with four Fs in there, sometimes it looks a little weird. I would have probably used P and I, maybe an F there and an E, but that's just me. So R in this equation, N is what we're trying to calculate. That's the number of other people out there, races we can out there we can talk to. R sub E, that is the average rate of star formation in our galaxy. Okay, how many how many stars are out there forming inside our galaxy? That's all that thing says. How fast is it going on? The fraction of those FP, that next one right there, is the fraction of those stars that actually have planets around them. Some stars do, some stars don't. At least that's the theory. Maybe they all do, and we just haven't found them yet. But some we know some do. We know some. We think some don't. The NE is the average number of planets that could potentially support life per star that has planets. So this is, hey, you have a star, it has planets. Can it support life? Can it not? And we are assuming life as we know it. Okay, so we're assuming, things that need water, that kind of stuff. F1, the fraction of those planets that can support life where it actually develops. So let's say you have a planet where you have all the right ingredients for life and it never actually develops. You got to take those out. Fi is the fraction of planets that support life. They then go on to develop intelligent life. Maybe they developed, fish and they never got past that point. Or maybe they developed dinosaurs that didn't die. I don't know. Who knows? Fe, I put C over here. I apologize for that. It's Fe, the fraction of civilizations that develop life that also develop a means of communication. So what we mean by communication isn't me talking to you, it's me transmitting things out so that it can be heard by other planets. So if you think back to prehistoric man or even a couple hundred years ago, we would not have had the ability to send information out and say, hey, look, here we are, let's chat, right? We don't have that chance. So the fraction of those civilizations that develop life is also and also develop a means of communication. That's important. L, the length of time they attempt to communicate with other planets. So let's say they develop the means to do it and they never bother. That takes them out. But let's say they develop the means to do it and they start trying and they just keep going. They keep trying to communicate with people out there. That length of time. So when it was first calculated by Drake, he took what I think is a very conservative approach. You can do the numbers for yourself. He took one star per year. The fraction of those stars that actually have planets, he took 1/5 to 1/2. Probably good numbers. The average number of planets that could potentially support life per star, he put 1 to 5. The fraction of planets that could support life where it actually develops, he took 100%. He said, okay, let's assume all of them do. The fraction of those planets that support life when we go on to develop intelligent life, he said all of them, 100%. Then how many of those develop meaning communication? He said 10 to 20. Okay, but even if you said 100, it doesn't change the numbers much. And what he found was the length of time they attempt to communicate, he took us somewhere between 1,000 years and 100 million years, right? So a long time. And I think he chose 100 million as that's when, you kind of expect these sort of planetary extinction events to take place or something. So he chose between 1,000 and 100 million. And the answer he got was n approximately equals L. So it's really just sort of how long do you try? And he got between 1,000 and 100 million uh, other civilizations out there. So You can adjust the numbers yourself, come up with your own equation. But even if you go back and change this, fraction of life that supports planet F1, change that to 10%, you only knock a zero off. So you still got 100 and 10 million. And if you change this to, support life and then go develop intelligent life, 10%, take it, you've now got 10 and a million. So you can adjust the numbers yourself and see what you come up with. But that is the Drake equation. Its whole point in life is to try to tell you how many other species are out there somewhere in the galaxy. Probably, we can't prove any of them because we never discovered one. But the other thing that's important to remember, and I looked it up, is the closest exoplanet that we are aware of is called Proxima Centauri b. It actually has the potential to have water. It's kind of in that zone from its star where it's like, okay, it probably could develop all the stuff we have here on Earth. So we call it class M or something, potentially. But it's also 4 light years away. So let's say we send a hello message. We go, hey, here, we're going to make a phone call. Boom, hello. And then it takes 4 years to get there. And they say, holy crap, somebody's there. Oh, hey, how are you? And it takes 4 years to get back. So 8 years just to have a greeting. It's a long time. That's assuming we're right. And the speed of light is the fastest you can go, assuming you can't go any faster than that. If you can, maybe we can shorten that time. But as far as we understand physics, you can't go faster than light. So you got a 4 year round trip just for communication. And you can't get a person, an entity to go that far, right? So, or that fast. So you're going to have to, if you want to send a human, you can get a whole lot longer than 4 years. But that is the Drake equation. Try it yourself, play with it. It's kind of cool. There's a really good Wikipedia article on it. But it's really just there to kind of convince you that there are probably civilizations out there in the Milky Way. But if you look at it from a practical perspective, they're so far away, it's tough to say by what we understand as the laws of physics that we could ever even have a phone call. So I hope you learned something. Please don't forget to click like and subscribe. Check out my playlist with the Nobel laureates. A whole bunch more stuff to come on the YouTube channel. We'll talk to everybody soon.